Hey everybody, it's Ripley back again. Okay, we've got everything in place. We've got limits, we've got continuity, we got everything. And now we're going to start talking about derivatives. And those of you that have already seen them and it's been driving you crazy going through all this madness about why are we talking about limits? Well, right now we're going to formalize the entire process by coming up with the definition of a derivative or an instantaneous rate of change. Now let's revisit what we talked about earlier in these topics. And that was the idea of finding the slope of the tangent line, all right? The slope of the tangent line. I want to find the slope of that guy right there. And hopefully you remember that the way in which we did that is we went on a fishing expedition, right? We threw a value way out here, and then we drew that value back with secant lines, right? Until we were theoretically so close to, in this case, a f of a, that we couldn't differentiate between the point and another point, and that should theoretically give us the slope of the tangent line, right? So we had all these secant lines, shunk, shunk, that drew their way back, but we needed a limit. So let's talk about that. Let's figure this thing out. What I'm going to do is I'm going to start at A, and our mathematical fishing expedition is going to get me out here to X, okay? Now, this point right here is going to be X, comma, f of X. If we look at the slope, if we look at the slope of that, of the secant line, then what would that be? That would be f of x minus f of a over x minus a, would it not? Do you agree with that? However, I don't want the slope of the secant line. I want the slope of the tangent line. So what do? I send x back to a. Well, what's the mathematical mechanism by which that happens? Well, you guessed it. It's the limit as x approaches a. Guess what? We just came up with what is referred to as the derivative at a point, or the slope of the tangent line. So we got lots of notation. This is slope sub tan. This is the derivative at a. That's another way of saying it. And it's also the instantaneous rate of change at x equals a. Now, if you recall, these guys, when we found the slope of the secant, this was the average change from a to x, average change. All right? Wow, that's super powerful. We got a lot going on here. Now, I want to incorporate something called you've already played with the difference quotient back in pre-calc, right? But I want to incorporate it. Let's see, let's pick orange here. I'm going to have the exact same function, but I'm going to use the difference quotient. So here we go. I got this guy, and here's my point a, f of a, right? And this is my function here, f of x. Now, instead of going out x, what I'm going to do is I'm going to go out to a plus h, which tells me that this little guy, this little increment right here, we're going to refer to as h. So now I have the point a plus h, comma, f of a plus h, right? You with me? And again, we're just going to start with the slope of the secant line. So the slope is going to equal, and it's going to be f of a plus h minus f of a all over, well, what would that be? That would be a plus h minus a, which is just h, isn't it? Now this little chunk right here, you may have seen this referred to back in pre-calculus as the difference quotient, right? This was the difference quotient, this guy. So we use the difference quotient to sort of set up our derivative. Now, what am I doing though? This is the slope of the secant line, right? This is the slope of the secant line. I need a different, I want the slope of, let's go back to our blue buddy right here. I need the slope of the tangent line. So what should I do on my fishing expedition? Well, I should run this point back to A, right? Well, how do I do that down here? How do I run points on the function? Well, don't I just let h shrink to nothing? If I take this point and run it back here, isn't that exactly the same thing as taking the limit as h goes to 0? Ta-da! And guess what? We have another way to represent f primed at a, which is pretty cool. Now, I want to do one of these with you, okay? I'm going to let's actually take a function and figure out the slope of the tangent line, excuse me, at some point. Okay, so here we go. Let's see, let's do f of x equals x squared. And we're gonna figure out, let's find the equation of the tangent line, at, let's go 2, 4. All right, so if you recall, the equation of a line requires a point and a slope. So I got my point right there for nothing. I could have just as easily said at x equals 2 and then we'd stick it in, but I don't want to insult your intelligence there. So what I'm really looking for is the slope. Well, what slope? Slope of the tangent line, right? Now, what we're going to do here is we're just going to follow this. I know that I'm going to try and find the derivative at x equals 2. So I'm looking for f primed of 2. Okay, so all I do is I'm going to do it both ways. It's going to drive you a little nuts, but it's good to see it. All right, f primed of 2 by this definition right here is f of x, which is x squared, minus f of 2, which is 4, over x minus 2, and I didn't give myself enough space here. I'm going to erase that just a little bit here and stuff some space. This is the limit. This is the limit as x goes to 2. Well, plug it in. I get 0 on top, 0 on the bottom. Do some algebra. This becomes the limit as x approaches 2, excuse me, of x plus 2, x minus 2, over x minus 2. We cancel, which just punches the hole in the graph. We don't care about the hole, we care about the limit. And this guy becomes 4, right, as I plug it in. Hey, guess what? This is the slope of my tangent. So I have, now I'm going to say this over and over and over again, particularly if you're in my class, my actual brick and mortar class, you're going to hear me say, look, there's 4 different ways to represent a line, really 3, but there's point slope, there's slope intercept, there's standard form, okay? Pick the easiest one. The easiest one is point slope. I can write this line as y minus 4 equals 4 times x minus 2. This 4 being the slope, this 4 coming from the point 2 squared. It's done. I didn't say find the equation of the tangent line and put it in slope intercept. If you want to graph it, it's usually helpful to put it into slope intercept, but I don't care about that, okay? However, if we were to graph these 2 lines simultaneously, we could probably relatively easily see, let's see, what would that be? Oh, this is weird because this turns into 4x minus 8 plus 4 is minus 4. So if I were to sketch y equals x squared, like that, and y equals 4x minus 4, what we're going to get is, oh, that's supposed to be tangent. We're going to get a tangent line. Whoops, wrong one. We're going to get a tangent line at 2, 4 that looks like that. You can check it on your calculator. All right, now I promised I'd do it both ways, so I'm going to do it both ways. You ready? I'm going to find f primed of 2, but now I'm going to use the difference quotient limit definition. All right, so this is going to be limit as h goes to 0 of f of a plus h. So this is going to be f of a plus h is what? Well, a is 2 and h is just h. So I have to do, ooh, yuck, 2 plus h squared minus f of 2, which we know is 4, right? This is 2 comma f of 2. So minus 4 all over h. It's a nice little setup, but we got to do a little bit more algebra. Now again, as always, let your limit follow you along until you take it. It sticks with you. So this becomes 4 plus 4h plus h squared minus 4 all over h. My 4's cancel. And if you notice what's left over is I have an h there. So I take the limit as h goes to 0 of, I can factor the h out. Because notice, well, wait, I got a little ahead of myself. When I plug h equals 0 and I get a 0 in the denominator, I'm immediately like, ah! If I plug an h in the top, I get 2 squared, which is 4 minus 4. So this guy turns into 0 over 0, which is bad. That tells me to do algebra. Sorry, I got a little ahead of myself. Now the whole point, just like the point up here of doing algebra was to get rid of the x minus 2, the point down here is to get rid of the h. I need to make that vanish, that h in the denominator. So I get h times 4 plus h over h, and hallelujah, those h's cancel. Now I have the limit as h goes to 0 of 4 plus h. And guess what that turns into? Yay! The same 4 that we got up here. Okay? That is pretty easy. Okay, let's see. What do I want to do here? We just did the line. Let's do one last thing and then I'll be done. Now, there are those among you who have had physics or have had a little bit of experience with differential calculus. And you're going to say to yourself, Dr. Ripley, what I would like to do is I would like to use my cheater methods. I would like to use my shortcut method. And to that I say, no way. You have to do the limit definitions, and it's not just to be punishing, which to some degree it might be a little of that, but it's also so that you understand how all of this f primed of a equals, and then we've got limit as x approaches a of f of x minus f of a over x minus a equals limit as h goes to 0 of f of a plus h minus f of a all over h. How all of this ties in, how the limits work, and for those of you who are going to take the AP exam, you need a great deal of limit definition of derivative. That's what these guys are called. This is called the limit definitions of derivatives. All right, you're going to need experience with that because you're going to see it. I think pretty much everybody who's watching this is probably going to take the AP. All right, now there's a general form that shows up. It doesn't get used very often, but it's good to mention because sometimes you'll see it notationally. All right, this is it's got a limit definition, but it's more theoretical. Okay, so this is wow, am I doing this? Instantaneous. Jeez Louise, I can't write that word for some reason. Rate of change, and I'm going to write it, and hopefully you won't freak out, but I'll try to elaborate a little bit. This is the limit as the change in x approaches 0 of delta y over delta x. Now, another way that you might see in a textbook from time to time is the limit as x1 goes to x2, or x2, let's do x2 goes to x1 just to be consistent in the way we used notations earlier, of f of x2 minus f of x1 over x2 minus x1. Now, these guys right here are the ones that are most commonly used. Okay? And I'm not going to ask that you memorize these so much as you realize what's really going on. All right, delta y over delta x is just slope. F of x2 minus f of x1 over x2 minus x1 is just slope. And then what are we doing? Well, we're letting the denominator go to 0. Well, why would we let the denominator in both of these cases go to 0? Because with limits, what that does is the denominator is the change in the x. If I let that go to 0, that is the numerical and algebraic equivalent of sliding that fishing lure back to the original point that we want to take a derivative at. Okay, so we just had a very beefy session. All right, it's very dense. What I want you to pull out of this is this. We have two ways to write limit definitions of derivative. This is notation for the first derivative. When you see that little prime, that means first derivative. I'm assuming you've all seen it. Perhaps you haven't. I'm sorry if I panicked you on that. This also represents the slope of the tangent line. So we got limit definition of derivative equals derivative, that's the notation, equals the slope of the tangent line at x equals a, equals the instantaneous rate of change at x equals a. All right? All four of those, well, 5 if you include this other limit definition, which gets used often, all 5 of those things have to be interchangeable in your head. You have to be multilingual when it comes to talking about derivatives in that way. Okay, I think that's it. Thank you for your time and your attention. I hope you have a good day, and I'll talk to you soon.